to group theory in the virtual Haken conjecture. After the talk today, there will be a break, and then Ian will give a more technical presentation of some of the details of the proof in case people are interested. So, Dennis, yeah.
Okay, thanks a lot. Thanks everyone for coming. Last lecture I didn't quite get to describing Wise's conjecture and his results. So the goal of this lecture is to first state Wise's conjecture and then describe some of the elements that go into the proof. And that will be rather sketchy, and as Rob is saying, I'd be happy to explain any details that people are interested in afterwards. So the plan for the talk is to discuss right-angled Artin groups, which I discussed a little bit yesterday, and then special cube complexes, and then I'll have all the definitions needed to describe Wise's conjecture. And then we'll discuss a little bit more geometric or combinatorial group theory, and I'll state the key technical result of Wise that I use in actually proving his conjecture, which is called the Mainormal special quotient theorem. I actually won't state the full, the general version of this, but just a special case to give the flavor. And then I'll outline the proof of his conjecture and then discuss some of the elements that go into it. And if there's time at the end, I'll discuss a few open problems. Okay, so
Theory, right?
in group theory. So I'll state it in the next.
Anymore, sorry.
Right, it's that's the conjecture that I proved that implies all these questions of Thurston.
Call it conjecture anymore.
Well, geometrization conjecture, I guess we'll.
Yeah.
This group has a mistake.
Oh, you found it. Okay. All right. So I wanted to describe the right-angled Artin groups, which turn out to be these sort of universal receptors for certain classes of fundamental groups of cube complexes. And they have nice properties that are inherited by subgroups, which is why I'm interested in them. So these have been studied for quite a long time in geometric group theory community, and Hagelin and Wise sort of brought out their importance in this aspect. So right-angled Artin group, you have a gamma, a simplicial graph. You have generators, which are just correspond to the nodes of the graph gamma, and then relators. If two vertices are connected by an edge, then we say that those two generators commute. So it interpolates between free groups, which have no edges, there's no relations for this group, versus free abelian groups, which are the complete graph. And if you take, for example, disjoint union of graphs, then you just get the free product of the two groups because there's no relations between the two various components. And you actually get certain three manifold groups occurring here. Some of these graph manifolds are actually obtained as right-angled Artin groups. And
The last time, which was not residually finite, with the four generators, and
yeah, that's
this one by that, and get that one.
I think that's actually this one right here.
Oh, really? Oh.
Yeah, I think so.
Oh.
Or the one with four chains is actually just the length 4 guy.
Oh. That's a group that has no finite quotients.
Sorry. That's a group that's not LERF. The Olympic rings one is not LERF, but it's residually finite though. If you take two graphs and then you take their join, so then the two subgroups corresponding to each of the subgraphs, you'll get you get the direct product of those groups. So it's closed under free products and under direct products. And actually, you get a three-manifold group if and only if it's a disjoint union of trees and triangles. So the triangle corresponds to the 3 torus. If you take a tree, you actually get a three-manifold with a boundary, which is like the Olympic rings kind of manifold, the fundamental group of the complement Olympic rings. Okay, so there's cube complexes associated with these right-angled Artin groups, non-positively curved cube complexes, namely the Salvetti complex. So for an Artin group A gamma, you can construct the Salvetti complex by you take loop for each generator, so corresponding to each node of the graph. And anytime you have an edge between two generators, you put in a little square that tells you that they commute. So you put in a commutator, a square representing a commutator for every pair of vertices that are connected by an edge in the graph. And then for every k-clique in the graph, you're going to put a k-torus there. So you attach a cube on, but you've already filled in the lower dimensional skeleton, so you can do this inductively if you like. Oh, clique is just a complete graph. That's just comma-torus. So a k-complete subgraph. Then you get one of these tori, and so this corresponds to a subgroup that's free abelian. So you basically throw in a torus for every free abelian subgroup that you see visually. So it turns out that the links of the vertices are flag simplicial complexes, and they're not quite. They're related to gamma. They're sort of obtained from gamma by a little doubling operation where you take two copies of gamma and you can cross some of the edges. But anyways, it turns out that, and then so flag complex is one that's determined by the one skeleton. So everywhere that you see the one skeleton of a k-simplex, then there's a k-simplex actually there. And that's the Gromov's condition for non-positive curvature, combinatorial condition.
So cubes satisfy that, or these cat zero cubical complex?
Yeah, that's right. So Gromov's condition is that they're locally cat zero if and only if the links of the vertices are these flag complexes.
Can you then put a metric on, so it's really a cat zero space?
That's right. So if you put the Euclidean metric on each cube and you just glue them by isometries, the universe of cover then will be a cat zero metric space. Yeah. So that's, again, this is in Gromov's 87 paper. So most of these group theory concepts were introduced there. So for example, the free group, you just get a wedge of loops. There's no higher relators. The free abelian group, then you just get an n-torus for the subeddy complex. And then somehow these Artin groups are interpolating between. So if we took a chain of three edges here, so 4 nodes, then for each of these edges, we're going to see a 2 torus. And we glue these 2 tori together along the wedge of 4 loops. And you're going to see this torus glued to this one along a circle, and this torus glued to this torus along the circle corresponding to A. So, and it turns out that this is the 2 complex that's a spine for the complement of the chain of 4 rings. So if you take the Olympic ring and remove one, then you get this is the fundamental group of the complement. That's a manifold, a 3 manifold. So those are some examples then of Salvetti complexes.
You keep putting in more cubes above the 2 skeletons?
If we had triangles here or something, then we would get higher dimensional cubes. So if you...
Torus there.
If it's... so this corresponds to the complete graph on n vertices. Then the Salvetti complex is the n torus.
Right. Oh.
Okay, so that's right-angled Artin groups and their Salvetti complexes. Now, Haken and Wise then introduced the class of what they call special cube complexes. Now, one way, they came about this from a different viewpoint, but one way of viewing these special cube complexes is you think about covering spaces of Salvetti complexes or right-angled Artin groups. What kind of cube complexes are they? Well, in a Salvetti complex, all the hyperplanes are embedded. So the hyperplane in a cube complex, the mid planes, yeah. So yeah. So you get those. It turns out in the Salvetti complex, you get a hyperplane for each node, for each generator. So if I chose, say, one edge, then I take the midpoint of that edge, and then in the square that contains it, I would take the mid square of that, which would give me a loop. And anyways, you get the hyperplanes in the Salvetti complex will correspond to the Salvetti complex of the graph obtained by deleting that vertex. So like in the n torus, if you take one of the vertices and delete it, you'll get an n minus 1 torus. So the hyperplane in an n torus would just be an n minus 1 torus. You take a hyperplane dual to an edge. And that's embedded, it's an embedded subcomplex. So if I take a covering space of something where all the hyperplanes are embedded, then the hyperplanes will still be embedded in that covering space. So there's some other conditions that hold for these Salvetti complexes. They're inherited by their covering spaces, namely, well, the hyperplanes are also, well, they're embedded and they're also two-sided. There's examples of cube complexes, like you take a Mobius strip made out of squares, then the midplane of that will be one-sided, and that's essentially how that can happen. So we assume that the hyperplanes are two-sided, and moreover, there's no self-osculating or inter-osculating hyperplanes. So what does that mean? Well, a hyperplane, so in a cube complex, you have this equivalence relation. We can regard the hyperplanes as an equivalence relation on oriented edges, where I say two oriented edges are equivalent if they're opposite sides of a square, and then take the equivalence relation generated by that. So I can look at an edge, and I can look at all the edges in the complex that are equivalent to that. So embeddedness means that there's no way you can go around and come back to another edge of this square that's not parallel, because otherwise the hyperplane would self-cross. I didn't draw a picture of that, but that's what it means.
You say take an equivalence relation edges, and then you talk about these other edges. I don't know what you're talking about.
Okay, so you can define an equivalence relation on edges that's generated by the relation that opposite edges of a square in the cube complex are equivalent, and then take the equivalence relation generated by that.
Yeah, but I think you're applying it to the whole fixed space and not just to the set of edges.
Just to the set of edges.
Huh?
Just to the set of edges.
Well, so then that has one equivalence class, the thing on the left.
So this edge here is equivalent to that edge because they're on, this is just a combinatorial picture, not geometric. So these lie on opposite sides of a square.
Yeah.
And then this edge is equivalent to that one because they lie on opposite sides of a square. So this guy, by transitivity, is equivalent to that one.
Yeah, so there's one equivalent.
And then, yeah. Well, these guys are equivalent. This guy is equivalent to that one. I didn't label them, though. So you also get hyperplanes crossing through each of these. So there's a hyperplane that goes around here and comes back, and now we have an edge. So this is called a self-osculation because it's coming back and sort of tangent to itself. And that's realized by you see two edges that come into a vertex that are in the same equivalence class.
I don't know how you're logically passing from the equivalent relation on edges to these mid-hyperplanes. You're not saying some sense.
Yeah, so the hyperplane is the midplane of each cube dual to that edge.
Right.
And then you extend these midplanes uniquely, and you'll see the dual, so I'm drawing the dual edges to each of those midcubes.
Right.
And then that gives if I continue that hyperplane throughout the complex, that's some immersed codimension 1 subcomplex.
Right.
It's not subcomplex, it's an immersed complex. And this equivalence relation on these edges is given, is combinatorially encoding those midplanes that are dual.
Sense to me. Although the picture is clear, but logically it doesn't make sense to me. Well, is equivalence class like one component or something of this midplane? Well,
That's right. So you can have multiple components of the midplanes. So that's right. So each of these equivalence classes give me a component of the midplane complex.
okay.
Is that clear?
Yeah.
Okay, good.
Why is that only a component? It's an equivalence class.
It's an equivalence relation generated by, so you get a midplane, so each equivalence class of these edges under this equivalence relation generated by opposite sides of squares gives a component of the midplane complex. So if we took this as a literal square complex, cube complex.
Like an irreducible component, the sense of algebraic geometry is Dimensional.
Yeah. So these guys are immersed, so they're crossing through each other, but they're different components. There's a map from this mid-plane complex to this complex.
Isn't there a mid-plane associated with this equivalence relation, or
Yeah, I didn't draw it in, but yes, it's.
isn't that some sort of one-to-one correspondence between maybe irreducible components and these equivalence classes?
Yes,
That's right.
Okay.
So there's one here, one here, one here, one here as well that I didn't draw in. There's a midplane. So a square has two midplanes.
yes.
And I didn't draw these other ones.
So the other one has two components, the red group and the.
Yeah, okay, so this guy, so this is not allowed in a special cube complex. Also, let's assume that this blue guy is an equivalence class of edges or midplane, and this is another midplane. Then if they cross in some square, then they can't osculate somewhere else. So this is called interosculation because they're crossing somewhere and then they're osculating here. So I haven't drawn it, but it can't. Yeah, you can't do both. Yeah. So the theorem of Hagen and Wise then says that if you have a cube complex that satisfies these special conditions, the hyperplanes are embedded in two-sided, they don't osculate, self-osculate, or interosculate, then there's a canonical locally isometric immersion to the Salvetti complex of a right-angled Artin group. And because it's geometrically a locally isometric immersion, it's a pi1 injection to a right-angled Artin group.
The words for that?
Yeah, so Salvetti complexes are examples of special cube complexes. Now here's another example of a special cube complex.
What's the theorem about it?
I'll just stay in the next slide, yeah. I got a little ahead of myself.
Okay.
So here's another example. Let's take a surface, and here's a set of walls on the surface. Codimension 1 subspaces, they form just a collection of curves, okay? Just literally these 6 curves, and I've just drawn them in colors to distinguish them. Now this is dual to a cube complex. The cube complex, Saghiev's construction in this case gives exactly the sort of Poincare dual tessellation of this surface, where you put a vertex in each complementary region, and you put an edge dual to each edge that you see there. So you think of this as like a decomposition of the surface into 6 hexagons, and then you're just taking the dual complex. That's a square complex. It's square because around each vertex here, when two of these curves cross through each other, it's degree 4. So you see a square. You can check that this is a square. It goes this, then to the back, and then there, and then back. So each of these guys is a square. So this is a square complex, and it turns out this is an example of a special cube complex. The hyperplanes are embedded, namely they're these curves, and then you have to check that they don't osculate. Like if I travel around this curve here, the equivalence class of these edges, they don't osculate around the vertices, and they don't interosculate or so they don't self-osculate or interosculate either. So this is an explicit example of a special cube complex. Now, associated with a special cube complex or any complex that has embedded walls or even immersed walls, I suppose, there's a so-called crossing graph where you have a node for each hyperplane, and I've color-coded them here. And if two of these hyperplanes cross, then you put an edge between them. So for each component, yeah. Okay, so the theorem of Hagen and Wise is that if you have a compact special cube complex and it has hyperbolic fundamental group, actually that's not necessary to get the first part of this theorem. Well, special cube complex, the fundamental group embeds into a right-angled Artin group. And it's given by a locally isometric immersion of the special cube complex to the Salvetti complex of the Artin group associated with the crossing graph. And quasi-convex subgroups of pi1x are separable. So quasi-convex in the sense of the hyperbolic fundamental group. So the proof for this then, you take the crossing graph associated with the complex X, like we just did here, and you get an associated Artin group. And then there's a natural map from the special cube complex to the Salvetti complex of that right-angled Artin group. because each cube here will be labeled by its sort of dual wall. So this edge here will be labeled by this red wall. This edge will be labeled by this blue wall, etc. And in the corresponding Salvetti complex, all the walls will be labeled by the generators, which correspond to the hyperplanes here. So there's a canonical way to map. For each square that you see here, there'll be a unique square in the Salvetti complex that you can send it to. And actually, everything's determined on the 2 skeleton. There's only one vertex of the Salvetti complex. Each edge will be dual to a hyperplane, will map uniquely to an edge in the Salvetti complex because everything's oriented, it's 2-sided. And then each square gets mapped in from the commutation relation, which is enforced by the crossing here. So there's a canonical way to map this special cube complex to the Salvetti complex associated with this crossing graph. And then it's this, what the special conditions are there for is to guarantee that this map is a locally isometric immersion. For example, if we had self-osculation, what happens, these 2 squares get mapped to the same square in the Salvetti complex, or the same edge, and that edge gets folded, and that's not a locally isometric immersion. So that's where this condition comes from. And here it's a similar kind of thing. If these guys have to go to 2 edges of a square, but if these guys if they don't share a square here, then they're sort of getting bent, and it's not a local isometric immersion. You've taken 2 sides of a square, so this map of a path is not a local isometry. So I'm assuming here there's no other square that adjoins these 2 edges. Then that's not a local isometry. So those are necessary conditions. The remarkable thing about their theorem is that they're also sufficient conditions for local isometric immersion.
Back on the
Yeah.
osculating, what if it flipped over so that the 2 arrows where it oscillated pointed in the same direction?
That's okay, it turns out. Yeah, so that doesn't cause this, because then this edge, it's mapped twice around a loop, and it's not bent. So it's still a local isometry. So that's allowed. Yeah, it's a good question. If you don't allow that, you actually get an embedding into the associated right-angled reflection group. So that condition can come in certain contexts. So okay, so you take the right-angled Artin group associated with the crossing graph, take the natural map. If those special conditions are enforced, then it's actually a local isometric immersion, and therefore it gives you an injection on the fundamental group. The associated, because it's a local isometry of a cat 0 space to a cat 0 space, so it's pi 1 injective. So you could apply this example to a Salvetti complex. I said Salvetti complexes are special cube complexes. This construction, if you apply it, it just gives the identity map from the Salvetti complex to itself and gives a pi 1 injection that way. So that's a special example of their construction. Now the subgroup separability, it turns out that it follows from certain subgroups of right-angled Artin groups are subgroup separable. Namely, there's a certain convexity condition. If they're represented by a locally isometric immersed cube complex, then it was proved by Hagelin that those are separable subgroups. So the subgroup separability here comes from a sort of geometric form of subgroup separability that holds for right-angled Artin groups. So okay, so now I can finally state Wise's conjecture that says that if you have a compact, locally cat 0 cube complex whose fundamental group is hyperbolic, Gromov hyperbolic in the sense that I was describing yesterday, then it's virtually special. So it has a finite-sheeted covering space, which is special. All the hyperplanes are embedded in the osculation or interosculation. So this is the importance of a hyperbolic fundamental group here is it's extremely important because there's examples of Berger and Moses that show that there's there's actually simple groups that are the fundamental group of a locally cat zero square complex, whose universal cover is a product of finite valence regular trees. So these examples are actually amalgamated products of two free groups. And they're simple groups. They're, the universal cover, well, a tree is a cat zero space. When you cross two trees, you just get a square complex that's cat zero. The links of the vertices will be bipartite graphs then. And this is a simple group. It has no finite quotients whatsoever, not even any infinite quotients, non-trivial quotients. And so it can't possibly be special or virtually special, can't have any finite-sheeted covering spaces. So what goes wrong here is that the fundamental group of this space is not hyperbolic, not Gromov hyperbolic. So, so that shows in this conjecture why the hyperbolic fundamental group is essential. So I proved this conjecture then 2012. So as I described then in the past couple lectures, this has the corollaries then of Thurston's questions 15 through 18 from his list. So if you have a closed hyperbolic three manifold, then the fundamental group is LRF, locally extended residually finite. Large means there's a finite index subgroup that surjects onto a free group, and then it virtually fibers. So it inherits this LRF condition from the right-angled Artin group, the theorem that I mentioned of Haken and Wise. So because these right-angled Artin groups have the locally, the quasi-convex subgroups are separable, then M inherits that condition. You also can separate the geometrically infinite surface groups from the tameness theorem.
Can I make a comment about this theorem?
Yeah.
I remember hearing him making these conjectures back in the 80s, but you know, when he was a graduate student, he made this picture of this curve winding around that you know, was on the poster. And when you take a manifold of fibers and you take the Riemann surface and go around, the monodromy map has a stable manifold that is approximated by such a curve. So this picture he was drawing when he was a graduate student in '71 is sort of describing all closed hyperbolic three manifolds virtually.
Yeah.
Amazing. I mean, he went right to the heart of the matter before he, you know, knew any of this stuff. I mean, in terms of material.
Yeah, and he actually didn't make these as conjectures because I think at the time there was so little evidence that he didn't have any reason to believe they were true. But over time, there's accumulated a lot of evidence for these questions. So.
Non-compact finite volume case?
Yeah, so the non-compact case, that's dealt with in Donnie Wise's paper, because those manifolds are Haken, and he's able to deal with the Haken case more directly.
I see, so he proved this for Haken manifolds?
That's right. Yeah, I think I took the statement out of here just for simplicity, but yeah, he proved that in his paper, and that's why I spent several years trying to understand what he did, because the implications were so important, or for me anyways. And then once I understood what he had done, then I realized some of the ramifications. So the proof of this theorem makes essential use of Wise's results, and I'll state in a few slides at least a special case of the main theorem that I make use of his. And part of the argument is based on my joint work with Groves and Manning. So I had mentioned in the last talk, some of my work with them on residual fineness versus LRF, and it turned out that those techniques were important in resolving this conjecture. And there's an appendix to my paper where we extend the arguments in our old paper. The results needed a little stronger statement that we proved. Let me just mention the fact about virtual fibering. So right-angled Artin groups, finite cover.
Fibers, yeah.
That's right. So there's a finite cover of M that fibers. And as I said before, hyperbolic here is also essential because there's certain graph manifolds that don't virtually fiber, like the unit tangent bundle to a surface has no cover that fibers over the circle. So right-angled Artin groups are residually finite rational solvable, and that condition implies that there's a finite sheeted covering space that fibers over the circle. So that's why. So these right-angled Artin groups, they have a sort of dual purpose. They allow you to prove that subgroup separability, but it was just maybe a coincidence, or it's some. I mean, for me, it was a surprise, anyways, that they ended up satisfying this residual solvability condition that implies the virtual fibering. So anyway, so that's sort of the logic of why this follows from Wise's conjecture. Yeah.
The manifolds of fiber with the fibers of torus, of course, they're not hyperbolic, but they fiber. And can they be included into this RAG?
Yeah, that's a good question. So the solved manifolds that you're describing, if you take, say, an Anosov homeomorphism of torus, take the mapping torus of that, that's a solvable group. It's not residually finite rational solvable, even though it's fibered. And there's certain other graph manifolds, namely, so there's a student of mine that proved that Yi Lu showed that a graph manifold satisfies this Riefers condition, or it embeds in a right-angled Artin group up to finite index, if and only if it emits a metric of non-positive curvature. So the non-positive curvature, so it turns out that, yeah, hyperbolic here is necessary, but it seems that non-positive curvature is really all that you need. And actually, the case of graph manifolds that don't have non-positive curvature, we still don't know, like whether they're linear, or we don't know much about them. A lot of those are actually fibered, but we still don't.
In dimension 3?
In dimension 3, yeah. But yeah, that's a good point. Yeah, there's that was actually a mistake I made in my original paper. I didn't realize that. I asked like which three manifold groups are Riefers, and I forgot about that case. But yeah, these solved manifolds are not Riefers. It's because when you pass the covering spaces, the first Bethe number never increases. It always remains rank 1. So
large.
Yeah. Okay, so now I want to describe some of the results of Donnie Wise that go into the proof of this theorem, and state the key theorem that he proves. So I need to describe amalgams and HNN extensions. So given groups A, B, and C, if we have injections of the group C into A and to B, then we can take the amalgamated product, which is given by sort of relative presentation. When you take A and B and you identify the elements in C inside of each of those groups. So you can regard it as a push-out or a universal kind of property. Then from combinatorial group theory, we know that A, B, and C all inject into this amalgamated product. And there actually exists an action of the group on a tree where the stabilizers of the vertices of that tree are conjugates of A or B, and the edge stabilizers are conjugates of C. And this is sort of a motivating example for groups acting on trees. So the quotient of this action is just a vertex labeled by A and B. So that's an example of a co-compact action of a group on a cat-0 cube complex. It's just one-dimensional. And actually, Sagiev's theory was sort of developed to try to find a converse to this. This group C is sort of separating the, it has relative multiple ends with respect to the group G. And Sagiev produces actually an action on a cube complex associated to any subgroup that has that property that it's sort of separates the Cayley graph into multiple pieces. It has more than one end as a relative subgroup. And so this is motivated by this kind of picture of amalgams. So similarly, if we can form a HNN standing for Higman-Neumann-Neumann extension if we have two subgroups of a group A that are isomorphic to each other. So we have an isomorphism between two subgroups. Then the HNN extension has the presentation like this, where we add an extra generator and which conjugates one subgroup to the other by the isomorphism. And again, the group will act on a tree with quotient just a loop. So it's another example of a group acting on a cat-0 cube complex. For example, right-angled Artin groups are all HNN extensions. More generally, any group with a surjection to Z will be an HNN extension of the kernel of that map by the conjugation acting on that kernel. For a right-angled Artin group, you have an HNN decomposition where you take any vertex and you take the graph, you remove that vertex from the graph, and you take the right-angled Artin group corresponding to the subgraph where you've removed that vertex. And this subgroup then will actually be both C1 and C2 in this case, and the stable generator will just say that it'll just commute with that. So the point is that V will, all the edges of the graph that it commutes with will be, so the extra generator that we add in the HNN extension will correspond to the generator of that vertex V, and the subgroup C will be the subgroup generated by all the vertices that it's adjacent to. So that's a simple case of an HNN extension where the stable this letter here is just the identity map from a subgroup to itself. So that's an explicit example of an HNN extension. And you can see this geometrically by taking the Salvetti complex and cutting along that hyperplane dual to the edge. Then that sort of geometrically realizes this HNN extension. So for example, if we apply this to the right-angled Artin group of the complete graph, then we just see the HNN extension of Z to the n minus 1 by the identity. So we add an extra generator and say that it commutes with everything in here, then we get Z to the n. Now, we can use these two operations to get non-trivial classes of groups, amalgamation and HNN extension. So we can get a so-called hierarchy for groups. So this originated in the study of one-related groups, the Magnus hierarchy associated with a one-related group, and then the study of Haken three manifolds by Haken. He introduced the notion of a hierarchy there in a more geometric context, but it has this corresponding group theoretic interpretation. So I'll say, so I'm going to define a special class of groups that have a hierarchy. So we'll say it's a class of word hyperbolic groups that QH standing for quasi-convex hierarchy. So they're defined inductively. Well, they have the trivial group, and then we can take HNN extensions or amalgamated products of groups that lie in this class, where the group is hyperbolic, and the amalgamating subgroup we assume is quasi-convex in the hyperbolic group G. And all the ABC we're assuming by induction, by our inductive definition, lie in quasi-convex hyperbolic groups. Then G will also be in this quasi-convex hyperbolic groups. So it's yeah, sure. Here or?
No, G's. So if A and B and C are quasi-convex hyperbolic and you form one of these G's, won't it automatically be hyperbolic?
So you have to be a little careful. So for example, if you take, say, C is a surface group, and you just take an HNN extension by some automorphism of a surface group, then that's not necessarily hyperbolic. So there's a Best-Fein criterion for when an amalgamated product of hyperbolic groups is hyperbolic that you need to apply there. But here I'm assuming, yeah, so I'm assuming it's quasi-convex in G, which is a strong assumption. There are weaker conditions you can put on this that would be enough to guarantee that. So one of the motivating examples then is if you have a closed hyperbolic free manifold, then it has a quasi-convex hierarchy. So its fundamental group is a Gromov hyperbolic group. It's has a quasi-convex hierarchy if and only if it's a Haken manifold, but with an embedded quasi-Fuchsian surface. So even like a totally geodesic surface in a hyperbolic manifold. So for example, the Seifert-Weber dodecahedral space that I described before, it has a finite-sheeted cover that it has an embedded totally geodesic surface. And that therefore has one of these, it has a covering space that has a quasi-convex hierarchy like this. Also, compact special cube complexes with hyperbolic fundamental group are going to have a quasi-convex hierarchy. Well, the hyperplanes are totally geodesic. In particular, the hyperplanes are going to be quasi-convex subgroups because they're totally geodesic in a certain metric, in the metric of the cube complex. And therefore, the hierarchy is obtained just by chopping along one hyperplane at a time until you get down to some contractible pieces. So those are motivating examples of these groups that have a quasi-convex hierarchy. So by this I mean the fundamental group of this hyperbolic of this cube complex, special cube complex. So this is sort of generalizing the category of these hyperbolic manifolds. So these are the class of manifolds that occurred in Thurston's hyperbolization theorem, a special case of the geometrization theorem that he proved. On the other hand, if you have a hyperbolic manifold that fibers over the circle, it's not necessarily, doesn't necessarily have a quasi-convex hierarchy because the fundamental group of the fiber is not a quasi-convex subgroup in the fundamental group of the manifold. It's a geometrically infinite surface group, and it's not quasi-Fuchsian, so it doesn't correspond to a quasi-convex subgroup. It might possibly have some other embedded quasi-Fuchsian surface. There certainly are fiber manifolds like that, but it might not. So what Wise proved in 2011 then is that if you have a group which has a quasi-convex hierarchy, then it's virtually special. So what I mean by that means there's a cat0 cube complex X. So cat0 I mean here is simply connected and locally cat0. It's globally cat0. So that G acts properly co-compactly on X. And there's a finite subgroup G prime of G such that this cube complex X mod G prime is a compact special cube complex. So we have a hyperbolic group that has a finite index subgroup that's the fundamental group of a special cube complex. So you start out with a quasi-convex hierarchy. Well, you end up with a quasi-convex hierarchy in this cover because it's special, and like I described, that has a natural hierarchy. But you get these extra conditions that come out of being special, namely you embed in a right-angled Artin group, you get subgroup separability, and you get these other nice things. So this is, and I haven't stated this in quite the full generality, so it also applies in the cusp case, but I didn't want to get into the technical relatively hyperbolic case. So note that, as I said before, oops, sorry. Yeah, so it's a group that is the fundamental group of a cat0 cube complex. Actually, you can have torsion, so the quotient might not be a cube complex, but let's assume it's torsion-free. Then this quotient, X mod G, is a locally cat0 cube complex. And this theorem is that if it has a quasi-convex hierarchy, then there's a finite-sheeted covering space of that cube complex that's a special cube complex. So it might have immersed walls or whatever, but you can find a covering space of that cube complex that has embedded walls.
X is not in this theorem, except it's related to these groups.
Well, X is, X is a cat0 cube complex. It's like the universal cover.
Oh,
maybe I should have put a tilde there, but
okay, it already is universal cover.
Yeah, and then G is acting properly co-compactly on that.
Okay.
I stated it in this way because G might have torsion in his theorem.
Right.
Oh, yeah, sorry. I guess G will be torsion-free because of the quasi-convex hyperbolic groups. There's a slightly larger class where you can extend down to finite groups, and then those might have torsion. But anyways, this.
Well, this is a globally cat0 cube complex, so X is connected.
It's the action's proper and co-compact, so this is locally compact cube complex. It's finite dimensional and locally finite. And the action's proper and co-compact.
X is simply connected.
Yeah, because it's globally cat 0.
Right. So this is related to G is essentially the fundamental group of X. So.
Yeah, it's the fundamental group of the quotient G mod X.
Yeah. Okay.
G prime is the fundamental group of X mod G prime. I don't know why I stated it this way. I should have kept with the. Yeah, but it might. Yeah, so in this case, it turns out G will be torsion free the way I've defined it. His theorem is actually a little more general than this. So this theorem then, it gives a characterization of so-called virtually special hyperbolic groups. So these are the ones that have this property. There's they have a cube complex that has a finite-sheeted covering space, which is special. And that's equivalent to having a quasi-convex hierarchy up to the finite index again. So
between groups and complexes, I'm not kind of getting.
Yeah, so
Cube complexes is supposed to be the universal coverage, represent the universal coverage.
That's right.
K-pi1 model of the.
Yeah.
It says cat 0. I mean, then it's.
Cat 0 is globally, it has to be simply connected.
Cat 0 cube complex.
Yeah.
Is you have this thing which you have this group which when you take this K-pi1, it's represented by a finite dimensional space, and that and the universal cover is represented by a cat 0 complex. Is that sort of the picture?
That's right. That's exactly the picture. Yeah. There's a little thing here. So there could be many different. In fact, there are many different complexes that G can act on. For each one of those, actually, this theorem implies that there'll be a covering space that's special. So that's not obvious, but it follows from the.
All right. This is.
So there's a covering space where all the hyperplanes are embedded.
Oh.
So you have these downstairs. You might have these immersed hyperplanes. They self-intersect. This theorem saying there's a covering space where all the hyperplanes are nice and embedded. So it's a generalization of the virtual Haken conjecture in some sense. But applying to sort of the class of Haken manifolds, but it's still a non-trivial result even for hyperbolic free manifolds. So he announced this in, I think, he had an electronic research announcement, I think, in 2009 or something, and then it took a while before it was disseminated. Here's a diagram. So his paper is 185 pages, and here's a diagram that he has at the beginning that describes the sort of logical implications there. So you can see it's somewhat intricate. It's a very intricate inductive argument. And actually, if you can read...
There's a lamination there.
Right. Yeah, it's kind of like this, there's this algebraic geometry book where someone mapped out all the implications between the various theorems. But yeah, somewhere in here, I can't even read this. Oh, it's just different parts of his proof. So the reason that he was interested in this was this Baumslag conjecture. If you have one related group with torsion, then he proves that it actually has a quasi-convex hierarchy, and therefore is residually finite, but you also get linearity and all the other corollaries that come out of being virtually special. So that was his motivation for this, and somewhere in here I think is the Baumslag conjecture, but I can't read it right now. So I wanted to give some indication of the key technical result from his paper. So this is proved like 2/3 of the way through the paper, and it's the key result that I make use of. So it's called the Mainormal special quotient theorem, but I'll just...
Reading this paper.
What's that?
Oh. Credit for just reading.
Yeah, I made my students suffer through that too in my seminar. So let G be a virtually special hyperbolic group, so like one of these groups with a quasi-convex hierarchy. And take any element in the group. Then there exists some power n, capital N, so that if I kill any power of that element that's a multiple of capital N, then that will also be a virtually special hyperbolic group. So, like say take a surface, you take a curve on the surface, this is saying there's if I kill a high power of that curve that's some multiple of some number n. Embedded curve? No, it could be a Merce curve. Okay. Then that will be a virtually special hyperbolic group. the hyperbolicity of this quotient goes back to Gromov's paper. So these hyperbolic groups have the property, they have lots and lots of infinite quotients. And you can get these infinite quotients by killing high powers of elements. In fact, you can even kill every power of every element if you take some correct power and you get an infinite torsion group, for example. That was proved by Olshansky. So they have lots and lots of quotients. And this can be proved using so-called relatively hyperbolic Dane filling, which is a technique developed by Groves and Manning and Osen. And that's the technology that we make use of. Wise, in his theorem, makes use of a different technology that he calls cubical small cancellation theory. It's a generalization of the classical small cancellation theory and combinatorial group theory.
Kill something higher than the sixth power, in some context, you'd always get an untrivial group.
That's right. Yeah. So that's a C prime. If it's greater than 6th power, then it'll be a C prime 1/6 group, and those are hyperbolic groups. If it's a free group, you'll just take say a one related group or something. So actually, we have a new proof of this theorem that replaces the small cancellation theory that he develops in his paper, which is about the first 100 pages of the paper or so, where he develops this theory with the sort of older technology of this relatively hyperbolic Dane filling that was developed by these guys in the early thousands or so.
If you have elements hyperbolic, then you only finitely many
non-hyperbolic.
They're not hyperbolic.
That's right. So there's so this can be regarded as a kind of generalization of Thurston's theorem in a certain context.
From geometry to group theory.
Yeah.
Right.
Yeah. So the general Mainormal special quotient theorem, I'm not going to state, but it's just to summarize, it allows one to kill certain controlled subgroups of virtually special hyperbolic groups, make sure that the quotient is still virtually special and hyperbolic. And these subgroups have to be malnormal and quasi-convex. So they're quasi-convex subgroups. So if I take a cyclic subgroup of a hyperbolic group, it's always quasi-convex and malnormal. So it automatically satisfies these conditions. But in general, I have to give these extra conditions. Malnormal means that it's as far from normal as possible. The intersection with any non-trivial conjugate is trivial. So, well, it turns out to be good from this context. So that's sort of what goes wrong in these Berger-Moses examples, that they're highly, they are an amalgamated product, but the group that they're amalgamating along is far from being malnormal. And that's sort of what makes those groups simple in some sense. So the theorem that is shown by, you show the quotient has a finite index subgroup which has a quasi-convex hierarchy. Not only is it quasi-convex, but it's actually a quasi-convex hierarchy where all the amalgamating subgroups are malnormal. So this is called a malnormal quasi-convex hierarchy. And then they apply work of Hagelin and Wise and Shu and Wise, which is another 60 pages, to conclude that the group is virtually special. So it's a very complicated inductive kind of argument. Okay, so I just wanted to give, so this is the key result that I make use of in the proof of Wise's conjecture. So that's, now I'll give a brief outline of the proof, and then we'll stop and take a break, and if anyone's interested in more details, I can explain whatever. So,
Before you go on,
yeah.
The logic here is, I mean, the theory here seems to be you start with one of these QH groups and you do something to it related to subgroups with some nice properties, and you get another QH virtually special group out.
That's right.
So
it's a complicated inductive argument.
But it's always starting with something that's got a hot.
That already has, you already can chop along something. That's right.
So how do you get into that world from?
That's what I'm going to explain now. Yeah.
Oh, okay.
Yeah, that's exactly the key. Yeah. So the proof of why is a conjecture. So remember, why is a conjecture is that if you have a cat-zero cube complex, compact cat-zero cube complex, locally cat-zero, with hyperbolic fundamental group, then it's virtually special. So we want to create this finite-sheeted covering space that is embedded in hyperplanes and whatnot. So the idea is that the hyperplanes complex will, and again, it could be disconnected. So, but it'll in general be immersed. If it was embedded, then we'd essentially be done. So if it's immersed, then we still have a cat-zero cube complex. So we induct on the dimension of the cubes. The maximal dimension cubes will be one less than those in X, because you've taken all these midplanes, which are one less than each of the cubes in dimension. So by induction, we can assume that the hyperplanes are virtually special. So even like the one-dimensional case, you start with a graph. The hyperplanes there are vertices. There's nothing really to do there. That's already special, so there's nothing to prove there. Let's go to the two-dimensional case. So the two-dimensional case, the hyperplanes are graphs. And so these graphs are...
Oh, the two.
So if I have a two-dimensional square complex, like that surface I showed before, the hyperplanes will be one-dimensional. They'll be graphs.
Right.
Those are already special. So we can assume that the hyperplanes are virtually special. And then by induction, we can assume that these are virtually special. Then I apply this result with Groves and Manning, which makes use of the Mainormal special quotient theorem, to conclude that there's an infinite sheeted covering space that's a regular covering space. So there's a normal subgroup of G such that the quotient some script G, such that the covering space has embedded two-sided compact hyperplanes. And here I didn't explain acylindrical, but that means the fundamental groups of these hyperplanes are sort of mutually malnormal. So if this was a finite sheeted covering space, then we'd be done, because we'd have these embedded hyperplanes, and then as a quasi-convex hierarchy, and then you apply Wise's theorem. But now I've just created this infinite sheeted covering space. So it doesn't seem like that much progress. But now the idea is that we're going to take this infinite sheeted covering space and we're going to chop it up. It has a hierarchy. It's an infinite, it's a finite stage hierarchy, but with infinitely many components and in the end. And what we do is we use the sort of combinatorics of this covering space to model a finite sheeted cover based on the hierarchy of this infinite covering space. So we take these sort of end game polyhedra that we get, there's infinitely many of them, but we assemble them, we sort of reverse engineer a hierarchy of a finite sheeted cover that's modeled on that infinite sheeted cover. So that's a quick summary of...
Or something? How do you...
Yeah, so there's a equivalence class of these various polyhedra that we get. So So we have a crossing graph of this covering space, just like we did in the compact case, and we make a certain graph. Well, we also want things to be joined by an edge if they intersect, if they have non-trivial intersection of the fundamental group. So we get a graph associated with this covering space, essentially the crossing graph for the hyperplanes. And we color these, coloring in the sense of graph theory. And we regard the colorings in this graph then you can regard it as a subset of the Cantor set. You have n different colors and you have the vertex set. And the colors, a graph has a coloring if there's a color associated with the vertices such that every endpoint of the vertex has a different, of an edge has a different color. So the claim is that, and then this group, script G acts on the X, so it acts on the space for these colorings. And the claim is that, well, these colorings give rise to a hierarchy. If we regard them as labels, we first cut along the guys labeled 1, then along 2, et cetera, until we get to n. So in the end, we get these sort of colored polyhedra that come from chopping up the cubes, and they'll have these colors on the faces. So these are just the stars of the vertices of the complex, and I call these colored polyhedra. So the idea of the proof is to reverse engineer a finite sheeted cover of it by reverse engineering a hierarchy, which is modeled on the hierarchy coming from the coloring of X. So we find a finite collection of these colored polyhedra, which has some kind of balancing relation. This is kind of like Thurston's reflection trick that in his geometrization theorem. So the number of colorings of a face is the same for two polyhedra that contain that face. And then you can glue the polyhedra together inductively. So you start gluing these polyhedra together to get a finite-sheeted covering space, which is then has a quasi-convex hierarchy and is therefore virtually special by Wise's result. So you get all these polyhedra, and there's these various colorings of the faces, and they match together in pairs. And it's set up in such a way that when I glue the last stage of the hierarchy, the next stages of the hierarchy are going to match up along the orthogonal faces. So I just wanted to describe briefly a lemma that's used in the proof of Wise's conjecture. So if you have a graph of bounded valence and a group acting co-compactly on that graph, then that action on the space of those colorings is an amenable action. There's an invariant mean on there. Oh, I see. I guess I'm already over time. We started a little late, but maybe I should save this for the next talk. So the claim is that the action on the space of colorings of a graph is amenable. And the proof is rather elementary. So maybe I'll start with that. We'll take a break now then. Okay. Yeah.
So you're making an infinite list of finite coverings, right? Or just making one? The inductive step.
One way of viewing it is you're making it so it's like a hierarchy of a Haken manifold, and you're the last stage of the hierarchy you end up with a bunch of balls. Then you glue those to, so we sort of reverse engineer. So we glue those together in pairs to get some handle body. You'll have the initial stage will just have a free group. So that is representing some infinite sheeted covering space of the manifold, because that's a pi1 injective subgroup, but we're only sort of gluing together a convex core for that covering space. So at each stage, we're going to glue together some of these polyhedra and get something that represents a convex core of a stage of a hierarchy of the covering space that we want to construct. So that's sort of what's happening here.
So a finite number of stages.
But yeah, the finite number of stages, which is given by the number of colors of this of the walls. And it's somehow modeled on this infinite sheeted cover. This infinite sheeted cover has the property that the walls are compact, and that's what makes things work in terms of getting the colorings and getting this amenability, and then getting a certain matching criterion to hold. So yeah, I don't know if that answers your question.
On the sidewalk.
Yeah.
So there's something like you have something like that, and then you're going to find some periodic average using this.
Yeah. Yeah. So that'll have an invariant. I think those have an invariant mean if you look at a space of these tilings.
Right.
Yeah. And that gives us the balancing condition. So you take this mean and then you approximate it by something which has rational values on the polyhedra and then integral values, so that if you look at a given face colored in a certain way, then the number of polyhedra on one side that has faces with that color will match up with the number of polyhedra on the other side that have faces with that color. And then you can glue that up. That immediately gives you the first stage of the hierarchy, or the reverse engineer of the hierarchy. The next stage is trickier because now things match up, but they only might match up to finite index covers. And then you have to work a little harder to get the next stages. So
15, how many minutes break?
Take a 15-minute break.
Okay.
take a little break. Okay. Thanks.
Okay.